All right, good morning, planar geometry. So it is Friday, and I apologize that I'm not with you today, but we do have the opportunity to go over some circle basics. All right, so follow along with me. We've got two main things that we want to figure out today. So the first of all is the relationship between tangents and radii of a circle. You probably aren't too familiar with a tangent, but remember a radii is plural of radius, and a radius is from the center to the outside of a circle. And then we're also going to use arcs, chords, and diameters of a circle to solve problems. Now, this is kind of a broad target. It covers a lot of what we're doing in this unit. And so in particular today, you're going to be looking for chords and some nice things that are going on there in a circle. Okay. All right. So first of all, you need some definitions. So first, for a circle, okay, a lot of people, if you ask them what is a circle, they would say, well, it's round, it doesn't have any corners, and things like that. And all of this is true. But the best definition of a circle is actually this. It says a circle is the set of all points in a plane at a given distance from a given point in the plane. So here's what that looks like practically. It basically says that you're going to pick a point on a plane. Remember, a plane is a 2D surface. And then you're going to pick all the points that are the same distance away from this one. So let's say we want this distance. Looks like maybe a centimeter or so. So I would go around and literally pick every point that is 1 centimeter away. And if I could draw, that would be even better from that point. Okay, and so those points make a circle. So interesting thing about the definition of a circle. Okay, so actually it's not the space inside of it. The circle is simply the line out here, all the points that are equidistant from the center. If you were to fill in the center of a circle, that's actually called a disk in geometry. So file away that fun fact. Okay. Another term you're going to need to know is a tangent. Okay. A tangent is a line that touches a circle at exactly one point. Okay. So it's a very short definition, but it's very powerful. Let me show you what a tangent looks like actually. This is what a tangent looks like. So here's my circle. Here's a point that's on that circle. This line comes through, touches the circle at that point, and then keeps on going. Okay. Basically what this does is it makes sure that this tangent line is never going to actually go through the inside of the circle, because as soon as it goes through the inside of the circle, it would need to touch the circle at 2 points, one where it went in and one where it went out. So since a tangent only touches at one point, it's going to just come in from outside the circle, touch it at just that one point, and then keep on going on. Same thing here. You've got your circle. Here's a point that's on the circle. This line is coming by, touching that circle at just that one point, and then going on. Okay. Now, to address this target, the relationship among tangents and radii. Super cool. Okay. So here's my circle. Let me go ahead and draw a tangent line, okay? So I'm going to put a point right here. I'm going to draw a line through that just touches that one point and then keeps on going. Okay? All right. It says draw a radius to the point of tangency. Now, where do you think the point of tangency is? You would be correct if you're saying, oh, it would have to be right there. Okay, so we're going to draw the radius all the way out to there. And you'll notice exactly what we found yesterday, which was that the radius and the tangent line are perpendicular to each other. Okay, so let me pull this off of the bottom here. Sorry, my recorder thing's messing up. All right, so here's that lovely theorem. A tangent line is perpendicular to a radius that is drawn to the point of tangency. Okay. All right. So let's do some application problems with that, because it's all well and good to know it, but you're going to want to actually be able to use it. All righty. So you are given that OT equals 5, XT equals 12, and OX equals 13. And we want to know, is XY tangent to circle O at point T? Okay, so let's go ahead and fill in some of this, because actually some of these lines aren't even drawn. Okay, so let me draw an OT here. Oops, that didn't look good. Let's try that one again. Let's back. All right, so OT is 5. That's going to go right there. And then we've got XT. That's actually this one right here. This is 12. And then OX is this line right here, and that's going to be 13. Okay. Notice what we just made here. Okay, we've got a little triangle going on. And actually, so I don't know yet that xy is tangent to circle O. What I'm trying to determine is it tangent? Well, based on that theorem that we just read, either we could know that it's tangent, and then we would know it's a right angle, or if you think of it the other way around, what if I can show that this is a right angle? If I can show that this is a right angle, that's going to be pretty confirming evidence that this must be a tangent line. Okay, well, how could I show this is a right angle? Well, I've got all three sides of this triangle, and we do have a way to test to see if a triangle is a right triangle, don't we? Yeah, we could set up the Pythagorean theorem. We could say 5 squared plus 12 squared equals 13 squared and test it to see if it's a right triangle. So when I test it, well, let's see here, 5 squared is 25, 12 squared is 144, 13 squared is 169. And I believe that gives us 169 equals 169. Ooh, so this is a right triangle, which means this must be a right angle, which means the radius is perpendicular to this line, which makes it a tangent. Okay, so under the explain your reasoning, that's exactly what you would write out. You know, the Pythagorean theorem shows that this is a right triangle. Since it's a right triangle, it means the radius OT is perpendicular to the line XY, which makes XY tangent. Okay, let's do another application problem here. It says given that OT equals 4, so OT right here is 4. YT, so that's this one right here, is 8, and OY, that's this one right here, is 10. Same question, is XY tangent to circle O at point T? Okay, so we've got a triangle again. What do you think? Same process? Sure. Okay, so let's set it up. So 4 squared plus 8 squared equals 10 squared. If 4 squared is 16, 8 squared is 64, and 10 squared is 100. I need to do 16 plus 64. That'll be 80. So I get 80 and 100. All right, are those two equal to each other? Nope. So since they're not equal, we don't know, or actually we know this is not a right triangle. And since this is not a right triangle, then this line can't be tangent. Okay, so to explain how you determine your answer, you would say, well, did the Pythagorean theorem, found out it's not a right triangle. Since it's not a right triangle, I know that XY is not tangent at point T. And it's as simple as that. Okay. We can also go the other way around. Okay, so let's say we're given that XY is tangent. So now we're starting off knowing that it makes a right angle. What is the length of YT? So this is what we're looking for. If OT is 18 and OY is 24. Well, remember what I said? We know that this is a right angle now because they started off telling us that XY is tangent to circle O. Well, if we know that, now we can actually use the Pythagorean theorem to solve for that missing side. Because notice you've got your two legs here. That's my hypotenuse. So that's going to be 18 squared plus x squared equals 24 squared. We can just go ahead and solve that. Okay. So 18 squared, I'm going to need a calculator. All right, so 18 squared is going to be 324, 24 squared. 76. I need to subtract from both sides. So I need to do 576 minus 324. Okay, so y squared equals 252. And then don't forget that last step where you take the square root of both sides. So x equals, and let me figure out how to do a square root here. There it is. All right, so 15.87, so I'll round that up to 9. Okay, so the length of this is 15.9, and I would agree with that. That looks about right. Okay, so just some ways that we can use the tangents to solve for some missing sides. Okay, here's the other thing that we would like to know. Okay, we would like to know something about the chords and how they affect a circle. Okay, And here's something kind of interesting. So let's say I have a circle and I ask you to draw two chords. So a chord is anything that has two endpoints that are on the circle. So like this segment would be a chord. This segment would be a chord. It doesn't have to go through the center. It could. The chord that goes through the center is called the diameter. But as long as it has endpoints on the circle, then it's considered to be a chord. Okay. Let's say I drew the perpendicular bisector of each of these chords. So perpendicular bisector means it goes through it at a right angle and it cuts it right in half. So like this segment right here, if I cut it right in half, there we go, and I meet it at a right angle, that is my perpendicular bisector there. Okay. Same thing over here. I'm going to try very carefully. Oh, nope, that's already going the wrong direction. Go through it at a right angle. Like that. Okay. So these are right angles. They went right through the middle of each of these chords. Okay. Notice where they meet at. That would be the center of the circle. Does that always happen? Yes, it does. Okay, so the perpendicular bisector of two chords in a circle intersect at the center of that circle. Okay, and that's something that you could use if you ever, had some type of circle that you were trying to find the center of, and you really don't have the ability to fold the circle or manipulate it like that. It's a nice one to use. Okay, all right. One final theorem that I'd like to introduce to you. Okay, when a diameter is perpendicular to a chord, the diameter bisects the chord. So let me draw a little picture of this for you. So I've got my circle. This is my diameter because it's a chord that goes through the center. And here's just some other chord, okay? I made sure that the diameter met this at a right angle. And so now we can know that this is being bisected. This chord is the same distance on both sides. Okay? It kind of feeds into, it would almost be considered, the word is corollary of the previous theorem. Because the previous theorem is basically saying, your two chords with perpendicular bisectors meet at the center. Well, now we're kind of doing it the other way around. You have a diameter, which has to go through the center. If it's perpendicular to the chord, then it also bisects it. Okay? All right, so how would we use that? Well, we would use it in something like this. Okay, you can clearly see you've got a diameter and you've got a chord. Okay, and so since you've got this diameter and this chord, and it says that it meets it at a right angle, that theorem now applies. So you know that this diameter is bisecting this chord. So if this part of it's 14, that means that this part of it is also 14. Okay? And since this part of it is also 14, could we solve for this missing side here? Well, we have a lot of experience with right triangles, and so we automatically see, well, we could set up a Pythagorean theorem to solve for that side. So that would give us 8.7 squared plus 14 squared, because those are both legs, equals c squared, because that's definitely my hypotenuse. Okay, and then we could solve that all out, and I trust that you guys are good enough at that you could take it from there. Okay, why would we want to do this? That might be a better question. Okay, notice what x is. Okay, it's from the center to the outside of the circle. That's actually the radius of the circle. I know it looks shorter than this one right here, but they're actually the same distance, because remember, all radii in a circle are the same length. So when you solve something like this, actually you can figure out the radius of the circle, which then opens up a whole new world of possibilities. We might be looking for circumference or area later down the road, things that we need to know the radius for. Okay, let me show you another one like that. Okay, so here's another one. I've got, it's going to be a diameter if this, went all the way through. Okay, it's meeting this chord at a right angle. So if this half is 10.1, that means this half is 10.1. Again, you can set up your Pythagorean theorem and solve for that missing side. Okay, something a little bit more involved would be something like this. Okay, so actually I'm going to ask that you open up the next video and watch how we would solve something like this. I'll go ahead and work this one all the way through. Okay, so see you in the next video.